Okay, good morning. Can you all hear me? Is the mic on? Yeah, okay. Good morning, thanks for coming. My name's James Molloy, I work for ARM. Today I'm going to be presenting alongside Anna Pazos from Qualcomm Innovation Center. And I'm going to be talking about what it takes to make LLVM as performant as GCC. And actually that title is the conference equivalent of linkbait. What I'm really going to be talking about is some work that our two companies have been doing for the past 6 to 7 months to try and improve LLVM's performance. And by doing that, we compared it to GCC. There. So the aim of the talk is to show you what we've done and talk about what we're doing now and in the future. And the work that we've done has been focused around ARM64, which is ARM's 64-bit architecture. And so the numbers I'm going to present today are going to be based around that. But actually, the problems that we found, the issues that we found, have been mainly target independent, or at least they affect multiple targets. So I'm really hoping it's not going to be an ARM-only talk and that everyone should be able to get something useful out of it. So the agenda for today, I'm going to talk about some background, give you some context of what we've been doing. I'm going to give you a quick overview of some of the problems that we've fixed already, and then talk about our current performance as we perceive it versus GCC for ARM64. And then I'm going to give a bit of overview of stuff that we're doing at the moment, so a couple of specific issues that we're fixing. I'm going to give a very dumb macro 30,000-foot view of the vectorizer and how that's performing. And then I'm going to hand over to Anna, who's going to talk, hopefully in some detail, about the Inliner and future directions there. OK, so let's start with some background. In January 2013, ARM open sourced the ARM64 backend for the first time. When we did this, it had support for scalar instructions only. It didn't support our Neon vector instruction set. And then for the next 4 to 5 months, we kind of hardened the code. We expanded our testing coverage and tried to make it more production ready. Come on, there we go. And then the next 6 months after that, we developed our Neon implementation. That's our vector SIMD engine. And about February 2014, we'd finished that. And at this point, we'd used our MC Hammer test suite, which we've talked about on previous occasions, to brute force test the MC layer. We're happy with that. We'd used our Emperor random test generation suite to stress test vector instruction selection and Neon intrinsics. We're happy with that. And we generally felt we tested it as much as we could. So at this point, we started looking at performance. But a bit of an aside first about our methodology and what we talk about when we talk about performance. We need some kind of target to tune to. ARM doesn't, well, we're not a direct consumer of the compiler that we create. Our partners and other people consume it. So we need some kind of proxy, because we don't have code that we particularly care about. And the proxy that we chose, first of all, was Spec 2000 and Spec 2006, both the integer and floating point parts. So there's about 23, 25 benchmarks in there. And at this point in February, GCC had about half a year of tuning on ARM64. So that's multiple man years. And of course, GCC has been heavily optimized for spec beforehand as well in their mid-end for other architectures. So we thought that a good way to start and work out where we can get to is to start with a differential analysis against GCC to work out where we're behind. So some caveats about what we did. We used fast math mode to get the best FP performance. We didn't look at the Fortran benchmarks for obvious reasons. We don't have a front end or libraries. So the results I'm going to show today are not spec. I can't say they're spec. They're not reportable. But they are still useful. I believe they are useful anyway. We started off looking at GCC 4.8 and 4.9, but later we did kind of a rolling comparison, bleeding edge versus bleeding edge. So all the graphs and stuff I'll show today are bleeding edge versus bleeding edge at the particular point in time. Also, I have a lot of numbers, far too many numbers and charts and graphs to show today. We analyzed on Cortex-A53, which is ARM's latest kind of small in-order core, and Cortex-A57, which is ARM's latest out-of-order core. But today I'm going to just focus on Cortex-A57, so I'm just limiting it down. Actually, we're slightly better on A53 than we are on A57. So we started looking at performance, and this is what we found. So on this graph, 100% means that there's no difference between Clang and GCC. Above 100% means that Clang is better than GCC, and below means GCC is better than Clang. So we're faster in one case, which is Hammer. I think we're vectorizing a loop that GCC isn't, which is great. But actually, we're generally pretty poor overall. over 5% behind GCC across the board, and with a pretty horrendous tail at the end of outliers. So there was quite a lot of work to do. So we just kind of sort of investigating that and looking at where we should be going when this happened. Apple open sourced their ARM64 backend, which is a backend for exactly the same architecture that they were developing in-house. And that happened around about the time of Euro LLVM in March, and that put us into a bit of a panic merge mode, where our number one priority changed from performance to ensuring there was only one ARM64 backend by the time of the 3.5 release. So luckily we managed that. Within 2 months, at the end of May, we'd halved the number of ARM64 backends back to a more reasonable one, and started looking at performance again. And this time, the numbers were a bit more rosy. So Apple have obviously put time into optimizing, which is great. So we're kind of a third of benchmarks we're ahead. We've still got that nice big peak and the one we're vectorizing that GCC isn't, and now we're 10% more ahead actually there, which is good. But there's still about 2/3 of a tail where we're behind, and we're over 5% on the last third, and there's still a few outliers as well. So there's still some work to be done here. So we analyzed them, and we started upstreaming stuff, and I'll talk about some of the stuff we upstreamed. I wrote this all out, and it took about 3 or 4 slides, so ridiculous amount of stuff. I can't talk about it all. And in fact, I'm not going to talk about all of this anyway. I'm just going to select a few things. We upped the maximum interleave factor from 2 to 4 times. So the interleave factor is what the loop unroller in the loop vectorizer will interleave in. And it becomes more risky the more you unroll. Especially with reductions, because you end up with a higher critical path at the end. So we had to give the unroller a few more smarts to work out when it's, well, more heuristics, basically. It sounds trivial, but actually it wasn't trivial. We swapped the order of the SLP and loop vectorizers, and that took quite a bit of benchmarking to check that was a good thing to do. What we'd found was in quite a few loops, we had a loop that was SLP-able and loop vectorizable. And because the SLP vectorizer ran first, it messed up the loop for the loop vectorizer. And generally, if you can use both, loop vectorizer will get you more benefit. So we swapped those around. Simple things like we implemented floating point subtraction reductions in the loop vectorizer that just weren't available before. Chad Rosier from Qualcomm did a bunch of work on making floating point reassociation work in fast math mode, so splitting critical paths, and so you can take advantage of higher instruction level parallelism. And again, Qualcomm did a bunch of work reducing sign extensions and truncation operations. This isn't just for ARM64, this is for any 64-bit architecture, because people tend to use 32-bit induction variables quite a lot. So you end up with lots of extensions and truncations when they're being used in pointer arguments and stuff, and Qualcomm spent ages tidying up a lot of that, so that was good. And we did some more stuff as well. So here we are today, we believe. As of 2 weeks ago, I kind of put my slides into code freeze 2 weeks ago, so it might have changed slightly since then. We're getting close to the halfway point now. There's still a couple of outliers that we want to try and sort out. I'm going to talk about those in a couple of slides' time. And I should mention that this is not just about the work that we did. I represented in the previous slide. That's just the work that us and Qualcomm did. A bunch of this is to do with people like Apple. So Gerolf's work on the machine combiner got us wins, and so does Quentin's work on cross-class copies. So this is the entire community's effort. And I would have really liked to come up here and say, and I was hoping to say that at the moment, what do we need to do to make LLVM as performant as GCC? Nothing, because we're on par, 100% geomean. But unfortunately, the GCC guys seem to have got wind of the fact that I was going to say this and started running away from us again. So in the past couple of weeks, they've started adding more optimizations, which I think is pretty unsporting of them. But yeah, we're working on regaining our lost ground. The more they improve, the more it shows us where we can improve as well, because we improve in different areas. They were doing some stupid code generation, which was masking some stuff that we could do. So it's not all bad. So now I'm going to talk a little bit about a couple of issues that we found that we haven't yet fixed. The first one I want to talk about is induction variable selection, which is quite important, especially in very small loops and especially on 64-bit architectures, because you've got more choices. So on the left at the top, we have a very, very simple function that has 2 induction variables, 2 pointer variables that are stepping up monotonically, and you've got a store to one of the address of the other. And that produces the code on the right. And what we really want to do is squash those 2 red instructions together to make the instruction on the extreme right, which is a store with write back. So that's a store where you do the store, and then you update the base register. Now, this is available on ARM, x86. Power has the STUX instruction, which does a very similar job, and apparently Itanium as well. So it affects multiple things. And we can't do that at the moment because loop induction variable selection has picked a very, very naive up-counting induction variable. You can see the compare at the end, x8. So we can't squash them together because it's doing something non-trivial with them. If it had picked the pointer, we'd been able to save an instruction here, which actually would give us quite a bit of performance improvement. So we've got a patch in progress for that, but it's not quite upstreamed yet. It's not in streamable quality. And then I'm going to talk about addressing mode selection. And by that, I mean selecting instructions to calculate an effective address. So the code on the left now is a little bit more complicated. It's a bit weird, actually, but this idiom is used in multiple spec benchmarks. What we've got is a linked list traversal, where every item in the linked list is looked up inside an array. So the red loads, you end up with you have to calculate the address for those. And because it's a linked list, you're not going up monotonically, so you've got to do a proper complex addressing calculation. And that's the get element pointers that are highlighted as well. And they're very, very similar. They just differ by the last offset. And then, oh, yeah, no, it's fine. This is the code that's generated. And we can see here that we've got the two red instructions, our multiply adds, which are quite expensive, really, in the whole scheme of things. And we have two of them, but they're identical. They're calculating exactly the same thing. And what's happened is the get element pointers is quite complex. We expand them very late. We expand them just before we go into instruction selection. And instruction selection is basic block only. So we don't get an opportunity, if they're in different basic blocks, to coalesce parts of what it expanded to. Or, even worse, hoist them outside the loops. So I see this happening a lot as well. We've got a patch submitted to fix this by How. I think it's about to go in very, very soon. And this affects all targets. So, for example, on x86, you get two LEA instructions here. I've no idea how that affects x86 performance, though. And the last thing I'm going to talk about is vectorization. And I said initially this is a really, really dumb overview of vectorization, and I wasn't lying. The donut shows all of the loops in Spec 2000 and Spec 2006 into an FP that GCC vectorizes. I've excluded the loops that only Clang vectorizes because I care about where we can improve Clang, not where we're doing better. And the blue part is where we also vectorize. So we vectorize the same things GCC does. Then the rest is quite interesting. So the red part is where Clang didn't tell me anything about the loop. And that could be because it completely got rid of the loop, or it turned it into a mem set or a mem copy, or it unrolled it. And that's generally OK, but when it unrolls stuff, if we completely unroll stuff before we even try vectorizing, then we don't end up vectorizing it at all, because the loop construct is completely gone. So loop vectorizer can't look at it, and currently the SLP vectorizer often doesn't look at stuff as well. So we can improve there. And then the green bit's quite interesting as well, because that's where the cost models differ. That's where GCC reckons it's beneficial to vectorize, and we don't. Now, it doesn't mean that we're wrong. GCC could be wrong. But I know there's at least some really interesting stuff hiding there where, for example, if we have sub-integer types like I8 or I16 vectorized, the cost model's completely wrong for that. It expects a bunch of truncations and extensions that just go away in CodeGen. So I know we can improve that. Then the rest is really interesting because that's all the different reasons that Clang gives why it couldn't vectorize the loop or it thought it wasn't legal to vectorize the loop when GCC evidently begged to differ. So I've seen a couple of reasons for this. I'm not going to go into the technical detail because I haven't looked at all 150 loops there. But I'm sure we can do better. So now I'm going to hand over to Anna, who's going to talk about the Inliner, hopefully. Sure, while we're handing over. I can repeat the question if you want. Yes.
So you compare to the number of loops that were vectorized by GCC, but are there some loops that we vectorize and they don't?
Yes, there are. I deliberately excluded that, first of all, to make the graphics slightly easier to comprehend, and secondly, because I'm trying to improve LLVM. So where we're doing better, that's all great, but I don't care about it at the moment. OK, thanks.
Good morning. So let's talk a little bit about inlining. During our GCC versus LLVM code analysis, we noticed that LLVM does not inline certain hot functions unless we increase the inline threshold. And we noticed that at O3 level and compiling some standard benchmarks like spec. In a separate experiment, using a larger, at least larger than the standard benchmark C++ Android application. Can you hear me? We noticed that LLVM produces larger and slower code at OS. So based on these findings, we tried to identify use cases that we think are very important to be considered in an inlining strategy to try to catch more of those hot functions. But before I get into the use cases, let's review some facts about the LLVM inliner. It's a SCC-based inliner that traverses the call graph in bottom-up order. As Chandler clarified in the mailing list, and you can read that in the source code, it's not a pure bottom-up inliner. It has this other mode, deferred bottom-up inline mode that sometimes kicks in. I'll get into it more into it in the next slide. And another observation is that the inliner cannot be modified to achieve a desired order of processing the call sites due to its path setup. So there is this entity, the call graph path manager, that sets the SCC the inliner will run on. So our first use case, we call it the primary use case because any other use case you can think of is kind of a variation of this one. And here we have the very well-known problem of A calls B that calls C. In a bottom-up inliner, the bottom-up inliner will always try to inline C into B first. But if C is inlined into B, B might end up being too big to be inlined at EA. And you can have a code layout that it's actually more profitable to inline B into A. And here I tried to highlight one possible example. You might have B, function B, that has a call setup, high call setup cost. So maybe getting rid of all this extra code for passing these parameters around is what would bring up the performance with inlining. So you want inline B. The current inliner tries to address this use case with the deferred bottom-up inlining mode. And in that mode, when it's attempting to inline C into B, it analyzes all the colors of B in order to see if they would be more profitable. And if they are, it skips lining C at that point, because eventually it knows we will end up inlining B into A. We think another way to address this problem, instead of delaying inlining a function, we can maybe have the inliner process the call sites in a different order. And maybe we can prioritize those call sites and present them in this different order to the inliner. The other use cases we have are other scenarios that we think it would be worth including in the inlining strategy. For instance, we would like to favor inlining call sites that happen inside loops. And another scenario is we would like to favor call sites at the root level of a caller instead of those call sites buried under several branch levels, which might have a lower probability of being executed. So with these few ideas in mind, loop depth, branch level, and processing the call sites in a different order, we decided to try a prototype implementation. And we call it the grid inliner. So we wrote a module path. We could have designed it as, as analysis path and many other ways. We chose a module path because for sure we know we would have access to the function analysis information we wanted to play with. So we started with that design. Grid inliner is not a replacement for the LLVM inliner. It actually builds on top of it and uses the LLVM inliner to do all the local inlining decisions of collecting information about call sites and the called function, computing and estimating the inlining cost, comparing that cost against a given threshold, and actually do the actual inlining work. So we have not touched any part of their code. Therefore, we think if there is any special tuning going on down there, they are preserved. But on top of that, the grid inliner allows you to set a different call site processing order. And that's achieved with a queue of call sites. Call sites have weights. And we have heuristics for computing those weights. And then we order that queue according to those weights. And we use several parameters to compute the weight. A couple of them are the size of the called function, how many times that function is invoked, the loop depth of the call site, and the branch level of the call site. We also noticed that for the workload we were experimenting with, the default inline threshold is kind of low to allow you to really inline some hot functions. But at the same time, we didn't want to go and change the inline threshold because that will have an effect on all call sites you are trying to inline. And you can have an increase in code size. So we allow the compiler in the grid inliner to specify an additional bonus policy for each call site. So it tries to catch some characteristics of the call site and produces a bonus value that can be added or subtracted from the threshold for that particular call site. And that helped us to catch more of some hot functions. So all these ideas, one of our engineers, Ima, tried to work them into an implementation, and we had some initial tuning done for ARMv7 target. At that time, we got some initial good results. We decided to upstream to collect feedback and start some code review process. And at that time, around that time, I think we also ran on A53 device. Then more recently, both Ian and I have been looking at enabling a grid inliner on AR64 A57 device. And we ran into a couple new issues which required a further tuning, which we are working on right now. At the time we upstreamed, we got a lot of feedback from the community, great feedback, to the point that we decided to have a live discussion about Inliner. So we proposed a BOF, and this BOF happens this afternoon. So anybody who has interest in the Inliner or experience in inlining optimizations, please join the discussion. In case you're curious about trying out the patch already out there and or just want to read it for review or work on the heuristics in the code, maybe having a view of the different objects and how they correlate might help you. So here it is. We have the grid inliner pass. As I said, it's a module pass, so it inherits from the module class. The grid inliner pass makes use of basically two objects, the inline cost analysis and a helper object named grid inliner helper. The helper is the glue between the grid inliner logic for computing weights and ordering call sites and the underlying LLVM inliner. We did modify the inliner interface a little bit just to have enough way to communicate with it about the call site we wanted to work on, the bonus policy we want to apply to that call site, and eventually when a function is inlined to retrieve back where are the new call sites exposed by that inlined function. So about results. Here we have some initial results at the time we upstreamed the patch. These results are from ARMv7 at 03 level. So here I'm comparing LLVM baseline, which has no grid inliner, against a run that has the grid inlining enabled. So anything above 100 lining means grid inliner helped improve performance, and below it, we degraded. So we have some interesting speedups of almost up to 8% in one case, and it slowed down about 2 to 2.5%. In the next slide here, that's the view we use to see what's the effect of grid inliner on code size. Here, I'm not showing the size increase of the executable size because sometimes to measure that, you have a really large statically linked executable, so the text section will be huge, and the increase caused by the grid inliner, sometimes you cannot, it's diluted over that bigger text section. So here we look at the sum of all the text segments in each of the object files that compose a benchmark. We might be accounting for some redundancy here that the linker might eliminate later, but this gives us a more quick way to assess where we are inlining too much, where we might want to work on the trade-off between speed and code size increase. So the final size of the executable, it's in 1-digit kind of percentage increase. So it's not as big as it appears from here. When we move to AR64 or A57 device, the first, at this point, we were not only building spec with a grid inliner, but we also tried to enable grid inliner on a large C++ code base we have access to. And the first thing we ran into was compilation time. There was an increase, substantial increase in the compilation time. Part of it had to do with some heuristics we were using that were causing more call sites to be candidate for inlining, and there was actually more inlining work going on. We also optimized how many, the way we were calling some looping info and the dominator tree type of analysis. So we changed the patch a little bit to make it more efficient there. And the other overhead, which we kind of cannot get rid of, which is inherent to any global prioritization scheme, is the fact that every time we inline a call site, we have to compute the weights of the new call sites introduced and reorder the whole queue. So there's no way around that. But doing some initial patches, fixes to the patch, we improved the compilation time, so it's not an issue anymore. We could go through that whole big LLVM C++ code base. And this is the result we see after updating the patch on spec benchmarks. So we still see some nice speedups of up to 6% in one case. And now, but we are seeing more degradation with AR64. In one particular case, about 7%. So this is still work in progress. We think there are ways to fix that degradation. This is another view of what happened to the size. It just helped us to see, again, where we are blowing, maybe potentially increasing the code size too much, and where we need to further look into. So where do we go from here? We have the BOF this afternoon. We hope, I'm sure we have a lot of theoretical discussions about LLVM Inliner, but I hope we also get some practical directions on what we can do right now to kind of get more performance out of the Inliner. Yesterday at the Hackers Lab, we had a very nice discussion with Chandler, and we have some pointers on what we can do. So this afternoon, we'll probably go over those discussion points as well. We have a very large list of internal bugs driven from our performance analysis effort. And when we review those bugs, some of them have to do with removal of redundant loads and hosting syncing loads and stores out of loops. And for some of those bugs, issues, we opened bugs with the community and got some feedback about those bugs. And it seems some of them we can resolve with some alias analysis improvements. And in one particular case, we even proposed a patch that kind of allows more aggressive optimizations when we have arrays of chars of constant size, which is kind of a pretty common type. In code bases. We propose a patch, it's being discussed, and we are trying to converge on a commonly agreed solution. So we have to do that for the other bugs we have as well. So we need help from the community to kind of close those bugs and see how much more we can get out of alias analysis improvements. Another experiment we ran is when you turn on the GCC strict aliasing rules, we see that improves performance in about 3%, it produced a 3% geomean speed up on spec. And we wonder if LLVM's strict aliasing rules will eventually get us to that level of allowing some more aggressive optimizations at the level that we see in GCC. So we'll probably engage with the community to see what's the roadmap for alias analysis and how much expectation we can have from gaining more performance based on this, the optimizations that it can lead into. We are continuing performance analysis. Now we tried to enable some other high-level, high-performance optimizations like LTO and PGO. And we are aware of diversifying the workload. We are not micro-optimizing for spec. So we do have access to other large C++ code base that we are trying the optimizations on. But if you look at everything I mentioned here and things that James mentioned earlier in the presentation, they might give us a couple more points in the geomean speed up. But how do we go even higher than that? Above 10% or maybe 2x speed ups. We are looking for collaboration with the community on implementing some high-performance optimizations. Maybe if you guys are working on optimizations that kind of exploit the power of 64-bit platforms or data layout optimizations. I know there is a talk later today on that. There are opportunities to do structure splitting. Some of the benchmarks that in the graphs that James showed are in the low end of not performing. So that's an area we would have interest in looking to. So if you are working in those areas and you are looking for collaboration, come see me, James, Janine. We are interested in talking. So conclusions. I think AR64 is a good example of successful cooperation between a bunch of companies like ARM, Quick, Apple, and the LLVM and Clang community. We had a backend that went through a major disruptive code-based switch. It got merged, stabilized, and now it's showing some signs of performance. That's good. Performance is very important for us. I hope it came across this presentation. We want AR64 compiler to be a competitive compiler, and performance is key. So we'll keep monitoring and reporting performance. And finally, we want to thank all the engineers that we get the pleasure to work with from ARM, Quick, Apple, and LLVM and Clang community. They are helping us move towards that performance goal. Thank you. See you in the afternoon.
Questions?
All right.
Okay, first off, thank you for all of your work you've done on this. This is really, really great analysis. Especially in the early parts of when you were showing some of the assembly and things like that, and this, to a certain extent, applies to the Inliner as well. But a lot of that sort of thing appears to me to be applicable to many of our targets. You mentioned x86 with LEA and things like that, that this is all problems in our infrastructure in either the middle end or our target-independent layers of the back end, like LSR is a prime example in my personal experience. Have you done any investigation as to what, if we fix these things, what the impact will be on ARM32? Or I assume that neither of you are too interested in what it does for x86, so, but ARM32 and Eagle and classifications like that.
I think, yeah, we have a slide, if you didn't remove. Oh, yeah. Do you want to talk about it?
Yeah, which one did you brought up? Okay, right. To answer your question, these are still AR64 numbers. AR64, at least from ARM side, is our most stable platform in terms of the development boards, is the most stable platform we've got. So we'll be doing all our analysis on that. We haven't got any AR32 numbers. As you say, most of the issues that we found, I did have a backup slide, but I think I deleted it, is in the mid-end. But most importantly, so it's mid-end and the target hooks into the mid-end. So heuristics and that sort of stuff. We found pretty much nothing in the back end.
Yeah,
Yeah, does that answer your question?
And usually when we find an issue, we try to change the code by hand and try to assess the performance. And here's, like for addressing mode, if we do those changes by hand, we can see some particular benchmarks speeding up that account for a geo-mean of maybe 0.4%. So that's how we do the analysis, like sometimes change by hand and try to assess in that target we are on to see how much it will what's the return of investment if we spend time trying to actually fix that fix that situation?
I think the real big fruit's in the vectorizer, personally. There's hot loops in a lot of these benchmarks I just looked into so far this weekend, where we're just not vectorizing some of the loops there. There's nested loops in the inner loops, and we're not vectorizing them, but we could. That's where I think we'll get most of the big wins.
Have you considered static profile? Two factors. One is static profile, another is register pressure while inlining. Register pressure is a factor because we experimented something last year, and probably we can discuss in the birds of the feather.
So you're saying
right.
You might inline too much and then start losing performance because you're spilling.
Right.
Yeah, we are not particular. We are on an architecture that you have plenty of registers on AR64. We have not run into that kind of analysis yet. Yes, definitely. Yeah.
Well, it's still applicable to AR64. I've personally seen lots of loops where we're spilling pretty horrendously. SROA produces a lot of live virtual registers and like 10 PHYs or something in a loop, and you can't keep all those live. So we are spilling. I haven't yet come to a conclusion of how we're going to fix that, but we've seen that.
For the inline specifically, there is no way to model call cost, for instance, right now. It has a rough estimate and a fixed cost that you attribute. And maybe if we can better model calling convention, we had a discussion with Chandler yesterday, maybe we can more aware also address register pressure and things like that in the inline. But right now it's
we try
to look at the collie, peak pressure in the collie, and then at the call site, what is the caller's pressure, and then we try to model it.
Yeah, it would be nice if you look how you could model that in the current LLVM line, and that would be a good contribution. That's something that we discussed yesterday about doing. It could help. Yeah.
And it's interesting because if you inline it, hopefully most of that will go away, right? That's the point of inlining. So you won't, taking the intersection probably won't give you the right result, because if you're just doing that, then why are you even inlining it? We have already done a bunch of optimizations to try and reduce register pressure and reduce spilling. So one of the things I did was make sure we never, we're a bit more careful allocating to queue registers. We would be vectorizing and do a load into a queue register, but actually we have no call save queue registers. So they all got spilled. So we've done some stuff. A lot of the stuff that Hao and Kevin have been doing with loop strength reduction is about reducing register pressure. Again, induction variable selection. We are producing naive upcounting induction variables in a lot of cases where we could use the pointer instead. And when we're very close to the register pressure limit, that makes a difference. So we're also working on that.
Have you considered the static profile counts if you're propagating across the call graph and then seeing
propagating
that?
What?
Yeah, let's assume that you had a slide where there's a inside a nested loop there was a call. Those calls can be made to be, using static frequency, I can say they are hot, right? Then I can make the inliner decision a little bit like favor those call sites, right?
Yeah, that's exactly what grid inlining is doing. And that's exactly one weakness in the current inliner, how to take branch level and loop depth into account when choosing call sites for inlining.
So this question is more for you, James. So are you looking at the ILP32 and the ABI for pointer compaction, and are you looking at that optimization also to get the pointer to be 32-bit and 4 GB?
We currently have no plans to look at ILP32 for LLVM.
You have no plans, or?
I currently have no plans. I can't say when we'll do it or anything. I'm not that high up, unfortunately. But currently we have no plans. It's not on our backlog.
GCC has already that support, right? So
GCC has prototype support. I'm not sure on the status of that or whether they felt it was beneficial enough. If you want to grab Matt Gretton down afterwards, actually, he can probably answer your question better.
Are you tracking code size and compile time too? So I work on Chrome, and we switched on x86 from GCC to Clang, and our experience Clang compiled way faster and produced smaller code and was almost as fast as GCC on x86. And for us, that was a pretty good trade-off. And on ARM, it looks like Clang is slower and produces more code, and maybe it's a bit faster, but we don't care about that all that much.
We're not from ARM's perspective, we're currently not tracking compile time. Obviously, we care about compile time. Any patch that we put in will be rejected if it increases compile time unnecessarily, so we do care about it, but we're not specifically tracking it ourselves. Code size, neither. So for the, we're not tracking code size. For our A-class cores, it matters a bit less. I mean, as long as it doesn't smash the cache, code size isn't your massive issue.
We started looking into code size in the context of the Inliner, and the application you mentioned is one of the ones we looked at. And with Grid Inliner, we got a little bit, we reduced code size by 2% and improved the slowness in some cases we were seeing too. So we started looking at the workload you mentioned, but in the context of inlining.
Okay, thank you very much for your time.
Thank you.